Alright, so let's work this problem. This is going to be, we're going to try to find equations for displacement and slope for a simple supported beam with a general load W on it. I like these problems because they're symbolic. Once we finish, we can have any load at any length. It's kind of cool. So the first thing we need to do in this method, the direct integration method, is what? What do we need? The moment. So how do we write the moment equation for this? If I were to cut this structure, say, here, at some distance x, I could find the internal moment, right? So what do I need to do that? Looks like I need the reaction at... You guys can play along. AY. Thank you. So I have a pin which has AY and AX. So let's find that first. So if I quickly sum moments about B, I should be able to find my reactions at A. Probably a good idea to go ahead and pencil in the concentrated equivalent force for that. What would that be? Yeah, it would be the area under the curve, which is height of W, length of L. And I'm going to do it from B, so what's the distance from B? Yeah, in the centroid would be L over 2. So I have all the pieces I need. So now when I sum moments about B, the concentrated equivalent force WL creates positive moment with a moment arm of L over 2. And then I have the reaction at AY, which creates negative moment with the moment arm of L. So this shouldn't be surprising, but AY is equal to what? WL over 2. Basically half the total load. It's distributed evenly to A, and if we sum forces in the Y, you'd see it'd be the same value at BY. So now, give me a second. I'm going to quickly redraw the free body diagram for this little chunk, the left side. I'll go ahead and put in my reaction, WL over 2. And we will have the distributed load, intensity W. And we're interested now in just the internal moment here, M, at a distance x. So what's our concentrated equivalent force here? Still the area under the curve, which is height W, length x. So we now have a variable force. And what's the distance to the centroid from the cut? Yeah, the length divided by 2, in this case, x over 2. So far, so good? Okay, so now we just need to sum the moments. So I'll sum the moments, again, right-hand rule. So we're summing moments at the cut and making sure it's in equilibrium. So I'll start with the actual applied moment. Using right-hand rule, that's a positive moment. What about the moment for the concentrated equivalent force? Positive or negative? Positive. And that'll be Wx times a moment arm of x over 2. And then I have the WL over 2 force, which creates negative moment. And it has a moment arm of x. So I'll solve for M. It should be a function of x. And I get negative Wx squared over 2 plus WL over 2x. Let's see if I can make that a little tidier. They have W and 2 in them, right? So I'll make this W over 2, and I'll end up with negative x squared plus Lx. Now we can check that, right? That should tell us the moment when x is equal to 0 is 0. And if I put x equals 0, that works. Also, when x is equal to L, what should the moment be? 0. So you put in x equal L, and it is 0. So it seems to work. So now we need to go back, and now we'll use direct integration. And the first part of that, the formula we just derived recently, was that the slope is equal to the integral of the m over ei term. So we know e. So I'm going to factor ei out, and I also have in my moment diagram this constant w over 2. So I end up with w over 2ei times the integral of the moment, and that moment is x squared plus Lx, and we'll integrate it over a little chunk dx. Is that okay? Did I make any mistakes? So I just have to do that integration. So, constant still there, 2 over ei. And then now I'll do my integration. So I'll have minus x cubed over 3 plus Lx squared over 2 plus my first integration constant. Let me put a little line there to kind of help visualize it. Sorry about that, I got kind of crowded. Do we know anything about slope in this beam? Do we know the slope at A or B? No. Somewhere out here in the middle, the slope would be 0, because we're going to start with a negative slope, go through 0 slope, and end with a positive slope. But right now we're not sure where that 0 slope will be. So until we find out otherwise, we have to leave C1 alone. So my second equation says that y is the integral of slope. So let's integrate this equation. So again, I have my w over 2ei constant. And I'll go ahead and integrate this. So this will be negative x to the 4th over 12 minus Lx cubed over 6 plus C1x plus C2. Now I've got two constants. I need two conditions. Now for this problem, the two conditions come from my support. So at the first support, at A, what does it say? Well, it says that the displacement at x equals 0 should be equal to 0. Yes?
Is the Lx cubed, is that negative or positive?
Should be positive, thank you. Okay, now point B, which is at x equal to L, the displacement should also be 0. So there's our two conditions. Mathematically, the easiest one to do is usually the one where x is equal to 0. So let's try that one first. So y at x equal 0, we know must be 0. Let's put in values of x equals 0 here. What am I left with? C2. So that means that C2 is 0. That was easy. Now, so far, all of our constants have turned out to be zeros, right? So you're getting the impression, oh, they're always 0. No. So at x equal L, we also know the displacement's equal to 0. Let's see what happens when we evaluate this at x equal L. So we get W over 2EI. X equal to L, that's what? L to the 4th over 12 plus L to the 4th over 6 plus C1L. And that should be equal to 0.
L to the third. Right?
Well, it's L to the 3rd here, but there's another L there. So all the terms have to be the same order. We couldn't add them together. So let's see. I'm going to rewrite that again. So let's look at this term first here. I'm going to put everything in terms of 12. So I've got negative 1/12 plus 2/12. That should just give me a positive 12th. So I have W L to the 4th. 12 times 2 is 24 EI. And that should be all this put together. And then I have plus C1L. And I know that has to be equal to 0. So that tells me that C1 should be negative WL cubed over 24 EI. So we're done. Well, kind of. So just plug everything back in. So that means the displacement as a function of x. Here's our equation. Where is it? Right here. We know C2 is 0, so I just have all this. So I'm going to start easy and see if I can make this work out. So I'm going to keep my W over 2EI term. So I'm just rewriting what I had up here. I'm going to add that to it. Let me forget that. Let's add it to it. So I'm going to take W over 2EI out. So I take the W, take the EI, I have 2 out. I'm left with minus L cubed over 12. Now, a lot of people don't like having these fractions in here. This is perfectly fine. You can stop. But a lot of people don't. So I can see there's a common denominator of 12 here. So I'll pull that out. So you'll get W over 24 EI. And you get minus x to the 4th plus 2LX cubed minus L cubed. And this is a more common way of writing the result. Hopefully it still works. When x is equal to 0, do we get 0? 0, 0, 0. No. Oh, I left off my x. Sorry. This is C1 times x. So there should be an x here. Now we get 0. Sorry about that. See that? Because it was C1 times x. Now at x equal L, does it work? Well, I've got L to the 4th minus L to the 4th plus 2L to the 4th minus L to the 4th. Again, that's 0. Now, where is the displacement maximum? So if you have a function generally and you want to find where it's maximum or minimum, what do? Take the derivative and set it equal to 0. Well, we have the derivative of the displacement. It's called the slope equation. So if I find where the slope is 0, then I'll know where the displacement is maximum. So what we would do here is we go back to this equation, which you can see is a cubic order, and we have to find the roots of that equation, which is not crazy hard, but you can do that. I'll tell you that it turns out to be L over 2. So you could find it. The other way to do it would be just to plot this and find the maximum. I've run out of time today. Maybe when we get back on Thursday, I'll show you how to take the derivative of this, which is the slope, find its value, and do that. Okay? All right.